Hello, everyone. Nice to see you guys.
Good afternoon.
Hi. Hi.
Yes. Hello. Good afternoon.
Good afternoon. So, how are you doing, guys? Hello. Yeah, good. So I guess that this, yeah, good that everything is okay. And I would like to mention you that soon we will have second midterm. So we will send some emails as notification, but just as a reminder, I guess this coming Saturday we'll have the midterm. So it will cover subjects up to this week topic on gravity. So gravity will not be included. So it will be until this rigid body rotation and conservation of angular momentum.
Excuse me, can you repeat? Will the gravitation be?
Gravitation will not be included.
All right.
So gravitation we will discuss during this week, but since this is the week right before the midterm, so it will not be included. It will be included already for the third midterm.
Now, what about previous topics like before momentum? Will they be?
Yeah, everything what is between the last topic included in the first midterm and until gravity.
Actually, there are 2-3 topics, if I'm not mistaken.
So there won't be any topics from the first midterm, like
No. For second midterm, there will not be. I mean, some concepts may kind of be there, but specifically to have problems on those topics, there will not be. Of course, second law of motion, for instance, is applicable in any cases, but problems will be focused on those topics which are, according to our manual, defined for the second midterm, and gravity will not be included. That's what we are going to discuss this week. Okay, I believe that most of you already have joined.
Also, can I ask another question?
Sure.
When exactly does the exam start? Like at what time?
The midterm?
Yes.
Oh,
because we actually have a history midterm at 12 p.m. on the same day. So I just wanted to know whether they will
that's a good point. Okay, let's check, because I'm afraid if there is some overlap, that should be something wrong done from the history side, because our midterms, they were approved with like vice deans for all departments, and that should be totally fine. But let's double check the time. It is actually in this manual for students, Physics 161, all. And folder for students. Let's go this manual. And let's see in this table. Midterm 1, midterm 2. So it is in the window from 10 to 11 a.m. So then I build.
So we'll have an hour. Okay.
It will be 45 minutes of active.
I understand. Just like
Have
an
this
hour
window.
between technically the window of physics and the beginning of history. All right, I get it. Thank you.
Okay, yeah, then it's okay. Then there is no overlap, which is good. Okay, so as I mentioned already, this week we discussed gravity, and from previous topics which we already went through, so we learned already kinematics and dynamics of translational motion, also kinematics and dynamics of rotational motion, rigid bodies. So we kind of know how to predict the position of bodies with known information of their initial position, velocity, acceleration. We also understand where this acceleration comes from. It's like topic of dynamics and laws of motion. However, it's still not a complete picture because we don't know the origin of certain fundamental forces, and gravitational interaction is one of these type of fundamental interactions. So that will be our topic of discussion. And let's say it's obvious that Moon is rotating about Earth, our planet, in a completely circular orbit, and there should be some force which keeps this our satellite orbiting Earth. Otherwise, according to the first law of motion, Moon should just move along a straight line with constant speed and just go away from the Earth. And if there is some force which keeps the Moon next to the planet Earth, there should be obviously some counter force according to the third law of motion, which will compensate this force. So there should be force and counter force simultaneously. And over time it came some fundamental realization of this understanding of the fact that the force which acts on the bodies on Earth's surface, and they fall down on the surface like this famous Newton's apple, and the force which keeps the Moon orbiting around the Earth, they have actually the same nature. And nowadays it could be quite intuitive from our point of view. However, if we think from the point of view of those early scientists who didn't have all this knowledge about the nature, it's not so convenient. It's also not so obvious to distinguish this unique features of such, from first point of view, very different interactions, but they actually possess the same nature. And the quantitative description of gravitational force interaction was first published in 1687 which is quite long time ago, by Newton with his famous Newton law of gravity. So I guess we will start from this law, our quantitative discussion. We will come back to this a little bit later after introducing three laws of Kepler's laws, and we will show how this actually was derived based on Kepler's laws. But initially, we will just write this equation and consider what it gives us and what it tells about gravity interaction. So let me switch to the presentation mode. And this Newton's gravitation law tells us that gravitation force is between two particles in any particles which possess some mass m1 and m2 will be proportional to their masses and reversely proportional to the square of distance between them. So here is some constant which was determined, quantified a bit later, which is the gravitational constant. So G is equal to 6.674 multiplied 10 minus 11, and units for this are Newton times meter square divided by kilogram square. So this is one of universal constants, and is required to describe this gravitational interaction between two bodies. So if we consider some body which is located on surface of the Earth, then gravitational force can be written as this gravitational constant times mass of the Earth times mass of the body on its surface. And then we consider that this mass of the planet is concentrated in the center of mass, which is in the center of the planet. And here will be the radius of the planet. So this is valid for the force on the surface of the Earth. And we know that this force, or the gravitational force, acting on the body with some certain mass will be equal to the weight of this body, and that is m times g, free fall acceleration. So from here we can already express g, free fall acceleration, which will be gravitational constant times mass of the Earth divided by radius of the Earth square. So we see that this gravitational, this free fall acceleration is not some fundamental constant. It depends on the mass and size of the planet. So that should be taken into account. And that is valid for the surface of the Earth. However, if we go higher, then we know that the gravitational force is reversely proportional to the distance square of the distance between two bodies. So here we have mass of the Earth, mass of the object, and here is r squared. So this distance, if we go away from the Earth's surface towards space, will be increasing. So it will be gravitational constant, mass of the Earth, times mass of the body. And here in the denominator, we will have radius of the Earth plus height, and that in second power. So in this case, it will be also some weight equal to weight of the body, but here it will be g at height h. So it will be a function of the height. So we can express g as a function of the height from the ground level, 0, next to the surface of the planet, to a certain height. Where this object is going, it will be equal to the gravity constant times mass of the planet, in our case it's Earth, and divided by radius of the Earth plus height in second power. So this acceleration of free fall is a function of height. It will reduce with the increase of height. So this h is in the denominator. So if we go like very far when h approaches to infinity, then g and weight of the body, we can put it here, mg, will tend to 0. So it will be condition like massless, like free fall condition when there is no any weight of the body. However, it is necessary to highlight that the realization of these conditions on space station is not because it's so far away from the Earth, because height is not so big for International Space Station. It's only like about 350 kilometers above the sea level on the Earth. However, the fact that it stays in this continuous free falling realizes zero gravity experience for astronauts on the International Space Station. If we calculate the value for the acceleration of free fall on the orbit of the International Space Station, it will be something about 8.82 meters per square second. And that is obviously smaller than the value at the surface of the Earth, but still quite big. So would not definitely result in any free fall experience. So now, with consideration of this gravitational equation derived by Newton, we will come back later to its derivation, but initially we just consider it as given. We come to the Kepler's laws. So those laws were not derived, so they are empirical laws, and they are based on pure observations, by the way, with naked eye, without any optical instruments. They were like results of observations for 16 years, and about like over 700 stars were monitored during these 16 years, and all objects moving with respect to these stars. And it took all this time not only for observation, but also for developing some mathematical models which can describe this empirical observations. So that was quite an impressive work and contribution at that time. And eventually Kepler came up with 3 laws based on this experiment, like continuous multi-year experiment. So first states that all planets move in elliptical orbit with the sun at one of its focus. So if we consider ellipse, so it should have 2 focuses, and sun should be in one of these focuses. So if planet is here, then it is moving. So this ellipse is the trajectory of the planet moving around the sun. So there are some characteristics of this ellipse, and one of the most important one is, we call it, let's say A, it's semi-major axis of the ellipse. There is also other characteristics like this B here, but it's not so so relevant for mathematical operations in the scope of Kepler's law. So this semi-major axis is the main characteristic, and also the position of the focus. Here is position C. So the difference between ellipse and circle, they are quite similar. However, the quantitative difference between these 2 forms is defined by eccentricity of ellipse. So it's some parameter E, which is equal to the ratio between C, position of the focus from the center, divided by the semi-major axis, A. So if, for instance, we have a case when this eccentricity is equal to 0, means that C is equal to 0. That means that the focus is located in the center. Then we have the case when ellipse is transformed back to circle. And if this eccentricity coefficient is not equal to 0, is larger than 0, obviously there is some deviation from perfect circle. It becomes more like elliptic shape. So first, Kepler's law states that orbits of planets are elliptic with more or less of this higher or smaller eccentricity coefficient, but all of them are elliptic. And now we can proceed with the second law. So second, Kepler's law states that it actually can be considered as some sequence of angular momentum conservation for isolated system. And it states that the radius vector drawn from the sun to the planet sweeps out equal areas in equal time intervals. So here is the radius, which goes from the sun, which is in the focus of the ellipse, to the planet. So in every like equal time intervals, this radius vector will move, obviously, because the planet is moving, and the area which is swept by this vector will be the same for the same interval of time. So let us try to kind of understand better why it happens and what stands behind. So when we have, let's draw it here, some elliptic trajectory of the planet. Here is our sun. Here is the planet with some mass mp. So it moves with some velocity vector, and probably I need to change the orientation of this velocity vector. So there is some velocity vector, and in order to keep this planet running on this elliptic trajectory, there should be some force, which is gravity force, interaction between the sun and the planet. So in order to understand why the radius vector sweeps equal areas of in equal time intervals, we consider that this system is closed, isolated system. And for isolated system, we know that the net external torque is equal to 0. So from other side, we know that net external torque causes change of the angular momentum, dl over dt. So if we have isolated system, this change of angular momentum is equal to 0, and angular momentum is constant. So now we also remember that angular momentum is equal to the vector product of radius vector and linear momentum vector. So it will be equal to radius vector times, we can put mass here, mass of the planet as a scalar. We can take it out from the vector product, and here will be velocity vector product. So in time interval of delta t, if we look here again on this elliptic trajectory, here is our vector r. Then in time delta t, there will be some change of this vector dr. So here will be next vector, and here is change dr vector. And the area in between, like this, swept by the radius vector, will be nothing else as the vector product of two vectors, r and dr. So this will be dA, some small change of the area, which is swept by the moving radius vector. And actually should be divided by 2, because it gives us area of parallelogram, which is built on these sides of which correspond to vector r and vector dr. But we are interested in the area of half of this parallelogram, swept by the radius vector r. So that will be, we can go to another slide. So dA will be equal to 1/2 of vector product r times dr. And we can also define this dr as velocity vector times some time interval dt. So we can substitute it here. It will be 1/2 of r times vector velocity vector times dt. And if we now compare this to the definition of the angular momentum vector, which we wrote previously. So we wrote that angular momentum vector will be equal to mass of the planet times radius vector times velocity vector. Then we can, keeping this in mind, we can write the following, that this is equal to linear momentum vector divided by 2 times mass of the planet. And this is times dt. So we kind of made this substitution, and we have this vector product here, and that's why we can substitute vector product with angular momentum, but instead we need to divide it by mass of the planet. And now we can rearrange this left and right part. So we can write the dA over dt, first derivative of the area swept by the radius vector, which defines position of the planet with respect to the sun in the focus of this ellipse, is equal to L divided by 2 mp. With this, we know that L is constant because it's isolated system. Mass of the planet is also constant, it doesn't change. Means that here in the right side, we have some constant value. And that tells us that the change of the area, which is like the area of the swept by the radius vector per each interval of time, which shows us the rate of the changing of this area, is constant. So it means for each interval of time, we observe that the radius vector sweeps this equal area on defined inside this elliptic trajectory, which proves the observation done by and analyzed by Kepler, and what is stated in his second law. So now we are approaching to the third law of Kepler's law, and that states the following. Let's go to the other slide. That the square of the orbital period of any planet, so means the time which it takes the planet to make one full rotation about the planet, about the sun, is proportional to the cube of the semi-major axis of the elliptical orbit. So the square of the orbital period is proportional to the semi-major, the cube of the semi-major axis of the elliptical orb. And in order to come to this statement from more quantitative way, let us consider some circular trajectory. So the third Kepler's law states that the square of this period of rotating planet about the sun is proportional to cube of semi-major axis. So now we consider some circular trajectory. We can do this because circular trajectory, circuit is some specific case of an ellipse when this eccentricity coefficient is equal to 0. So let's assume that here we have mass of the sun, and here is our planet. So it possesses some velocity vector v, and here is our radius position vector. So we know that there is some force, gravitational force between mass and the planet. And another force which counterbalances this force is centrifugal force. Centrifugal force is a product of mass of the planet times centripetal acceleration. So we have gravitational force is equal, if we consider just magnitudes, mass of the planet times this centripetal acceleration. So in the left side, we have gravitational force. So we have already equation for this gravitational force, which is universal gravity constant times mass of the sun times mass of the planet divided by radius square. And in the right side of this equation, we can write that here we have mass of the planet, and centripetal acceleration can be in terms of linear velocity, can be given as v squared divided by r. So we discussed this in previous discussions. We also remember that from circular motion, that velocity, linear velocity, is equal to omega angular velocity times radius. In other ways, since here we deal with the period, not with some angular velocity, we need to go from angular velocity to period. Who remembers how we do this? How we can write angular velocity in terms of period? Any ideas?
Two pi r divided by t, maybe.
2 pi divided by t. So 2 pi divided by t and times r. You are right. Okay, thanks. Then we can substitute this instead of linear velocity in our equation. So will be g. Here we can also cancel out this mass of the planet. And here we have also r and this square cancel. So then we have the following: g times mass of the sun divided by radius is equal to 2 pi radius divided by t squared. And continue here. It will be 4 pi squared r squared divided by t squared.
Excuse me, can I ask?
Yes, sure.
Velocity is equal to 2 pi minus t, but why you multiplied it by radius?
You mean here?
Yes.
Okay, so linear velocity is equal to angular velocity times radius. So instead of angular velocity, we express it in terms of period of rotation, which is 2 pi divided by t. And then we multiply by radius.
All right. Thank you. I got it.
Okay. Yeah, so new just frequency, like how many times per second rotation happens, that will be just 1 over t. But angular velocity, that will be 2 pi divided by t, or it's equal to 2 pi times mu. So how many radians per second the object is moving around about some axis in rotational motion. Okay, so now what do we have? Actually, we can let's express from the last equation t squared, because we need to have t squared in the left side. So t squared will be equal to 4 pi square r. Actually, we will put r out of the parentheses. 4 pi square divided by g ms, mass of the sun, and here will be r cube. So we see that in the parentheses we have just a constant, 4 pi constant, g is universal gravitational constant, and mass of the sun is also a constant. So if we consider this constant, let's name it some k times r cube. So we see that t period of the rotation along this elliptical orbit in second power is proportional to the radius of the, it's actually circular trajectory in this consideration specific. In order to make it mathematically more easy to derive, is proportional to the radius in the third power, which also valid for the semi-major axis of the ellipse. If we substitute this circular trajectory with an ellipse, then this radius can be substituted by a cube. So because we, if it's true for specific case of ellipsoid elliptic trajectory, which is circular trajectory, then it also valid for other forms of ellipsoid trajectory when eccentric coefficient is not equal to 0. So with this, I think that's everything what I wanted to tell you for today. We introduced the gravitational equation derived by Newton. also introduced three laws, the Kepler's laws, and in details describe, like explained where they come from. Our next discussion on Wednesday, we will start from using these three Kepler's laws in order to show how originally Newton derived this universal gravity law, this equation which we introduced at the beginning. So we will see that it was enough information obtained just from empirical naked eye observations summarized in three Kepler's law to derive this equation which describes quantitatively gravitational force. So that we will continue next discussion. If you have any questions, you're welcome.
Where did you get a cubed divided by a cubed? The final form.
Oh, sorry. So that if we good point. Let's make it more clear. So it's not divided by a cube. It should be written that this particular case is derived for a circular trajectory. But if we go for extrinsic coefficient larger than 0, so we go from circular trajectory to elliptic trajectory, that will be also valid for t square is equal to k, some coefficient constant times a cube. So we just derived it for circular trajectory, and then a became r. But it's easier to do for circular trajectory. That's why we went for this. However, it also valid for ellipse trajectory.
All right, thank you.
You're welcome. Okay, then thank you very much for attention. Have a good day. Take care. See you on Wednesday.
Thank you. Goodbye.
Bye.
Thank you. See you.
Thank you. Goodbye.